Okay, in this interesting one, we're really dealing with kinetic energy is really what we're kind of dealing with. So it has a flywheel, and they give us the I for the flywheel, 1/2 mr squared. So it must be a solid disk. We know that solid disks have that 1/2 for the K value. It rotates about an axis that's perpendicular to the disk. That's not really important. And basically, they're talking about flywheels being used to store energy in the form of rotational kinetic energy, or that angular kinetic energy, as I said it should be. So they mentioned that gasoline burned in a 300-mile trip is about 1.2 times 10 to the ninth joules. So this is actually what we're going to put in as our kinetic energy. So kinetic energy is going to be 1.2 times 10 to the ninth joules. The 300-mile trip is actually irrelevant. So we want to know what angular velocity would a 13 kilogram flywheel with a radius of 0.3 have to rotate to store this much energy. So what we're borrowing here is that angular kinetic energy is equal to 1/2 I times omega squared. So we're after omega. We want to try to figure that out. So the thing I have to plug in here is I. So the first step is let's figure out what I is. So I is 1/2 mr squared. So this would be 1/2 my mass, which is 13 kilograms, times the radius of the flywheel, which is 0.3, and then just don't forget that that is actually squared. So this is our I, so we've got that value. Once I calculate that, that can go in here for I, and then the idea is you're going to set it equal to this value, so the only thing missing will be omega, and you'll try to solve for it. Now if you notice, it says give your answer in radians per second and revolutions per minute. When I solve this, and I say that omega equals something, if I put my I in kilograms and meters squared and I have my energy in joules, I will get this to be radians per second. So that one's automatically going to be there. So how do I go from radians per second into revolutions per minute? So we've done this before, we've just did it the other way. So what we're going to end up doing is we're going to put 2 pi on the bottom because there are 2 pi radians in a revolution. And then we're going to also multiply. We've got the 60 or the seconds in the bottom. We want to put minutes down there, so we're going to put 60 up top. That'll cancel out the seconds and put 1 minute on the bottom. So in essence, what you're actually going to do is you're going to take your answer of radians per second, you're going to divide by 2 pi. Now again, I would put parentheses around it to make sure that you actually get it together, and then you're going to multiply by 60. So multiply by 60 and divide by 2 pi. The opposite way of how we converted out of revolutions per minute, we're converting into revolutions per minute. Hope that helps.